Here we have the integral from 1 to the square root of 3 of the arctangent of 1 over x dx. We don't have a product here, so it may not be obvious that we're going to use integration by parts, but we don't have an antiderivative for the arctangent of x. So this is going to act kind of like the natural log. I'm going to let u equal the arctangent of 1 over x so that dv is equal to dx. Let's go ahead and get that v is equal to x. We have that out of the way. Now we're going to differentiate the arctangent. du is equal to, now the derivative of the arctangent is 1 over x squared plus 1, but our argument is 1 over x. So our derivative is going to be 1 over x, that thing squared plus 1. Don't forget that we were going to use the chain rule. The derivative of 1 over x is negative 1 over x squared, and then we need our differential dx. Now, du can stand to be simplified before we move on, so we're going to take a moment and do that. Du will then be equal to, if we distribute x squared in the denominator, and the denominator has 1 over x squared, we're going to clear that complex fraction. This is going to become the negative of 1 over 1 plus x squared. Again, for the first term in the denominator, we divide out the x squared. For the second term, we just distribute, and we end up with x squared times dx. Our original integral using the integration by parts formula then becomes uv, so x times the inverse tangent of 1 over x. We're going to write down that that's going to be evaluated from 1 to the square root of 3, minus the integral of v du, but du has a plus sign, or a minus, excuse me, so that becomes a plus. The integral from 1 to the square root of 3, and then v du is then going to become x divided by 1 plus x squared dx. This may look like we're worse off because now we have something, I mean, we used to have just one function, the arctangent of x. Now we have here this x over 1 plus x squared. It's still one function, and do you know how we're going to proceed? We're going to use a substitution. If I let t equal 1 plus x squared, then dt is equal to 2x dx. You may be like, why don't I use u equals? Folks, we've already used u in this problem, and I don't want to use it again. In this case, now I need to multiply and divide by 2, so I have 2x over 1 plus x squared, and then 1/2 out front of that integral. Now I effectively have 1/2 times the integral of du over u. That's going to integrate to the natural log. I'm not going to do the full substitution. I'll just integrate it as is, because I frankly don't want to change the limits over, and I would have to if I did that. Putting this together, we have x times the inverse tangent of 1 over x plus 1/2 times the natural log of 1 plus x squared. Whole thing is evaluated from 1 to the square root of 3. You may be thinking we need absolute values for the natural log. We actually don't. The argument is 1 plus x squared. That'll never be negative. Evaluating this expression for the square root of 3 is going to give us the square root of 3 times the angle whose tangent is 1 over the square root of 3, and that's going to be pi over 6, plus 1/2 times the natural log 1 plus x squared, if x is 3, is equal to 4. Minus what happens when we put 1 in place of x, and that's going to be 1 times the angle whose tangent is 1, so that's pi over 4, plus 1/2 times the natural log of 1 plus 1 squared, and so natural log of 2. Now this looks pretty messy, but we can simplify it just a little bit here. 1/2 times the natural log of 4 is the same thing as the natural log of 4 to the 1/2, which is actually the natural log of 2. So we, believe it or not, have like terms. Natural log of 2 minus 1/2 times the natural log of 2. That's going to give us 1/2 times the natural log of 2. You could write it as natural log of 2 to the 1/2 or even square root of 2, but generally it's fine, leave the 1/2 out front. But then we have this other bit to deal with, which is positive pi times the square root of 3 over 6 minus pi pi over 4. This could be left this way, but I prefer to get the common denominators just because it's a way to combine the pi's, really. And so we have 1/2 times the natural log of 2 plus 2 pi times the square root of 3 minus 3 pi all over 12. And that's how I'm going to present the final answer here.